Oh, good morning, everyone. So I'm Cleber, here from the Physics Institute of São Carlos. And so thanks for the introduction. So thanks for inviting me to be here today and tomorrow. I just realized that, oh, I remember you from another school, right? No? No, man, I'm sorry. You look like someone that I met in a school 1 year ago. Okay, not you. So we can be introduced later. So I just figured out that tomorrow I only have 30 minutes, and then I make like an arrangement with Christina, so she gave me 45. So I had to readapt my talk. So let's see how it goes. So basically, today the idea is, since it's a school, I will talk a little bit about some basics or some fundamentals on ultra-short laser pulses, a little bit of nonlinear optics, an introduction to nonlinear optics, and then some applications on ultra-short pulses and nonlinear optics that might be related to biophotonics or not, okay? So here I work in the photonics group. So basically, in our group, we work in several research areas, so basically using nonlinear optics and ultra-short laser pulses. So we do some nonlinear spectroscopy of organic materials and polymers, and the idea there is to develop materials for applications, either in biophotonics or photonic devices. We also work on developing novel methods for nonlinear optics, control of light-matter interaction by pulse shaping, and also the use of femtosecond lasers for micromachining and microfabrication. So here it's the summary of my 2 talks. So today I will give an overview on ultra-short pulses, and then tomorrow, or a part of today, I will talk a little bit about applications. So every time I think about laser pulses, the first thing that comes to my mind is this picture here, right? Since I was a kid, maybe, I'm a big fan of Star Trek. And so if you're not familiar, that's the Enterprise NCC 1701E, which actually is the one from Captain Picard. And basically here, what they are doing is that they're firing a Borg cube, which is somewhere here, right? So if you look it up on the internet, you see that the size of the Enterprise are exactly, the length is 685.3 meters. Look for the details there. The width and the height, okay? So if I take the Enterprise as a scale bar, and then they're firing here the photon torpedoes, right, against the Borg cube. So if I take this size here as the scale, then the length of my light pulse that actually the Enterprise is firing is about 15 meters. Of course, as I know the velocity of light, I can calculate how long in time is my pulse, which in this case is 50 nanoseconds. So as you guys might be aware, so the Star Trek happens in the future. It means that in the future, right, in the 24th century probably, they are using Q-switched lasers. So they're using 50 nanosecond lasers to actually kill the Borg, right? Which actually makes sense, because if you want to make more damage, you usually want like longer pulses. But as we know nowadays, we have picoseconds or femtosecond pulses, which of course are much higher in technology. Okay, if you're not a big fan of Star Trek, as I am, so maybe you go for the Star Wars. So if you're Star Wars kind of people, okay, I'm fine. So that's the Death Star, right? So the Death Star, as you see, Star Wars people, they are not like that precise. So they don't have information about the size of the Death Star, this kind of thing. But okay, you can get the diameter of the Death Star is about 120 kilometers, about. So see, they're not precise with numbers. So if you take here, then you estimate the size, and then also they have some pulses there. They are about 3 kilometers, right? And then the duration of the pulse for the Death Star is about microseconds. Okay, so as you see, the technology that they're using in Star Wars is much worse than the one in Star Trek. Okay, I don't want to go in any debate about this. Also, but there is some funny you know, like phenomena happening here, right? Because there's light coming, and somehow the light is concentrating and going towards another direction, interacting with nothing, right? So that's got to be something very hard to understand in my point of view. Okay, so that being said, so that's the first thing that comes to my mind. So that's maybe the reason why I decided to do physics and working with lasers. So there are, of course, several ways to get laser pulses. So maybe the first one is by doing some excitation with some so one first idea would be to use some pumping the active medium with some short flash lamp, for instance. So in this case, what you have there is something in which your flash tube here is actually flashing on the order of 1 microseconds, for instance. And in this case, you can get reasonable short pulses. And by short pulses, in this case here, it's a pulse which usually is complex, right? And basically, the pulse will be as long as the excited state lifetime. So that's more or less how short can you get when you actually use a short flash lamp in this way. So just for you guys to have an idea, so when you have solid-state laser media, in this case, the lifetime is on the order of microseconds. So with this kind of technology, you usually get pulses in this ballpark, microseconds to millisecond range. Another way to get laser pulses is by the so-called Q switch. So in this case, what you do is you actually switch. So Q switching comes from switching the Q factor of the laser cavity, right? So basically, Q switching here means that for some time, you prevent lasing, right? So the cavity loss is very high, on the order of 100%. So actually the cavity is closed, but at the same time, so while the cavity is closed, you keep on pumping the cavity. You keep on exciting the laser medium. And then in a given point in time, you abruptly open the cavity, so you see the cavity loss decreases to almost to 0. And then, of course, you have the laser emission at that time. And then that's the way you usually get a Q-switched pulse. So Q-switched pulse means that you actually switch the Q factor of that cavity there. So usually with this kind of technology, you can get pulses whose duration are limited by how fast you can switch the cavity, so how fast can you open and close the cavity, the round trip of the laser of your cavity, so how long does the photon takes to make a round trip on the cavity. And so in general, usually this technology allows you to get 100 to 10 nanosecond laser pulses. So how do we actually go then for picosecond or femtosecond laser pulses? So the idea then is to use what we call mode locking method. So the mode locking, basically, as we know, in a laser cavity, we have several modes here, represented here by those sinusoidal waves. So if they are not on phase, so if they are not in phase one with another, in the end of the day, you get something. So if you look at the intensity profile, in this case here, by the interference between all those longitudinal waves you have in your cavity, you see no pulse, because the interference is such that there is no phase correlation. Then you have no pulses. So that's what happens when you have a continuous wave laser. However, if by a given mechanism you are able, for instance, to lock the phase of all the modes you have inside your laser cavity for a given time, here you have a nice superposition of those waves in such a way that you get a pulse, right? And that's got to be repetitive, right? So what I'm trying to say here is, of course, at this point, for instance, it's out of phase, so the interference is got to be such that I have a minimum. But for a given point in time, you have a maximum interference. So that's the way you get an ultra-short laser pulse. So you have to find out a mechanism, of course, to lock the phase. I'm not going into much detail, so if anyone wants to talk about that, we can discuss how are the methods actually to lock the phase in the so-called mode locking laser systems. So that's how nowadays we get picoseconds or even femtosecond lasers in our labs. Something that's very interesting about ultra-short laser pulses is that there is a relationship which is actually related to the Fourier transform in such a way that when you have a continuous wave, so in time the intensity is constant. It means that in spectrum you have a delta function. So when you have a continuous wave, there is a single frequency in that laser, right? Of course, if you have an ultra-short pulse, which in time is very short, so it's a delta function in time, of course, in spectrum, it's got to be very spread out. So you have all colors. In principle, you have like if you have a delta function in time, it means that you have all colors in frequency. That, of course, is the uncertainty principle. That's actually related to the Fourier transform. So in real life, what we have is actually that the spectrum or the width, the spectral width of your pulse is related by the inverse with the duration of your pulse. So for instance, for a long pulse, in time, it's got to be something like this. So in spectral, in frequency, it's something short, and vice versa. So if you have a short pulse in time, so in spectrum, it's a kind of a broad pulse. So what I'm saying here is usually, although people say that lasers are monochromatic, when you're talking about picoseconds, not picosecond, but let's say femtosecond lasers, they are not really monochromatic. Just to give you an example, if you have a 150 femtosecond laser pulse, right? In the infrared, near infrared, it has about 10 nanometers of bandwidth, right? So if you have a laser which is 800 nanometers, it means that you have light from 790 to 800 something. All right, okay, 10, more or less 10, right? So if you make shorter pulses, like 30 femtoseconds, the bandwidth is on the order of 50 nanometers, right? So they're not really monochromatic, right? They have a band. And as shorter the pulse, wider is the spectral band of that pulse. So here are some of the materials that have been mostly used for femtosecond lasers. So maybe the most famous one is titanium sapphire, which is this guy here. As you see, it goes from the 600 nanometers all the way to 1 micron. So it goes from the red to the infrared, and some other materials such as chromium YAG, chromium forsterite, and so on and so forth. Of course, every time we're dealing, then, because of this broad band, this broad spectral band of ultra-short laser pulses, we have to pay a lot of attention for dispersion. So, of course, now we have several colors in our pulse, so dispersion plays a role, different from when you use CW lasers, continuous wave lasers. So in that case, you don't care too much about dispersion, or you don't care at all about dispersion because you have basically a single color. And then, so dispersion, in the sense I'm saying here, is basically the dependence of a refractive index on the wavelength, and then, of course, it causes angular dispersion, so it disperses the beam in space, right? As Pink Floyd already knew, right? If you see, right, the disk of Pink Floyd, that's it, right? So, okay. And then, of course, you have the group velocity dispersion. Since the index of refraction is different for different colors, so the group velocity is got to be different for different colors. So in a given pulse, for instance, the red travels faster than the red part of the pulse travels faster than the blue part of the pulse. So you get the chirp, right? For those of you that already work with femtosecond laser pulses. So I don't know how many of you have seen the titanium sapphire laser in real life, but here's a picture. That's a titanium sapphire crystal being pumped by a neodymium laser, second harmonic of a neodymium laser, the green light here. And this is the emission, actually, of the titanium sapphire crystal. And here, so the absorption in the green, and that's the emission of the titanium sapphire. So usually, with titanium sapphire lasers, you can get pulses from 20 femtoseconds all the way to 100 femtoseconds. OK, and then it comes to the question, because you have such a broad spectral band, right? So if you can deal with the dispersion, which is not easy, as you can figure it out, right? It's not easy to compensate a dispersion that broad. But if you can actually deal with dispersion, you can get very short pulses, right? With this bandwidth, you can go all the way to 20 femtoseconds, more or less. OK, so now it comes the question, how short is a femtosecond? Of course, the easy answer would be 10 to the minus 15 of a second, right? Which doesn't make sense. OK, it does make sense. But, I mean, that's not a real feeling for us, right? It's like to be, OK, I'm a billionaire. I'm a trillionaire. I don't know. There's so much money, right, for my real expectations in life that I don't know if someone that has, so how much richer is someone that has 1 billion than someone that has, I don't know how many billions, right? It's something that you don't have a feeling. So one way to have a feeling of how short is a femtosecond pulse is by doing something like this. So 1 minute, OK, we have an idea of how long is 1 minute, right? Is 10 to the first of a second. A camera flash, milliseconds, more or less. A Pentium clock, nanoseconds. 1 month, 10 to the 6th of a second. The age of the universe, 10 to the 16th of a second, of seconds. A 10 femtosecond light pulse is something around here. So basically, 1 minute is to the age of the universe at the same time as 1 minute is to the 10 femtosecond. So that's how short is a 10 femtosecond laser pulse. OK, if you like this, it's OK. I like this one better. So as a physicist, we like to see, right, the pulse itself. So this is the electric field representation of a femtosecond pulse. So as you can see here, it's a 20 femtosecond pulse. It goes from minus 10 to 10 femtoseconds. This pulse is at 800 nanometers. So it's a pulse in the near infrared, 20 femtosecond long. So, OK, what's nice to see here? The electric field only, so we know light, right, is an electric wave. So the electric field only oscillates 1, 2, 3, 4, 5, 6, 7, 8, maybe 9 times. So 20 femtoseconds at 800 nanometers is so short that the electric field only oscillates a couple of times, 8 times maybe. So that's how short is 20 femtoseconds. There's no enough time for having, I don't know, a huge number of oscillations of the electric field in the electromagnetic wave. So nowadays in our labs, we have lasers going all the way from hundreds to 20 femtoseconds, as I mentioned before. And one thing that we can get with femtosecond lasers is that we can get very high light intensities, because the light, the energy, actually is concentrated in a very short time duration. So you can get laser intensities on the order of 100 gigawatts per centimeter squared easily in the lab. So that's not even difficult. You don't sweat at all to get this kind of intensity in our lab if you use a 100 femtosecond laser pulse, for instance. Just to give you an idea on how intense, that's not really correct, but to give an idea, right? So a laser pointer like this one here, if you would calculate, the intensity is on the order of 1 milliwatts per centimeter square. I'm saying that's not really correct because I'm kind of comparing continuous wave light with a pulsed light, but the number is nice enough to be shown. And so you see, that's 10 to the minus 3, and in there is 10 to the 11th watts per centimeter square. So I'm talking about a factor of 10 to the 14 times more intense than what we have with this kind of laser that I have in my hand. Okay? So what happens when we have such kind of intensities? The intensity of the electromagnetic field of your light is so high that you actually start seeing some nonlinear optical phenomena. And then I'm going to try to explain what is nonlinear optics, right, in here. So basically, in a very general way of saying, it's basically a study of optical phenomena that occur when you have very intense light. So basically, you need lasers. But not any kind of lasers, right? You need in general, is easily if you have pulsed lasers. It's much easier if you have ultra-short laser pulses. So how does it show up in physics? So it shows up as a nonlinear constitutive relationship. So basically, as some of us, at least the ones that actually took physics, we know that the polarization is proportional to the electric field as a first approximation. But in that case, usually the susceptibility chi is a constant, right? It depends on the frequency, but it doesn't depend on the electric field. It doesn't depend on the intensity. So usually this is a constant. In nonlinear optics, basically the susceptibility presents a dependence on the electromagnetic, on the amplitude, of the electric field. And that gives rise to the fact that some optical properties will now be dependent on the light intensity. So some properties that before were constant with the light intensity, now they depend on the light intensity. Just to give you some historical facts, although it seems that nonlinear optics is something very new, because it, of course, relies on lasers and ultra-short lasers, actually in electromagnetism, it has been shown, for instance, in magnetism since 1923, and saturation of the population. That's a work from Purcell and Blumberger from Harvard in 1950s, saturation of luminescence in 1940s, right? So that's some nonlinearities in electromagnetism. That's not really with light, let's put it this way. So the first demonstration of a nonlinear optical effect is by Professor Franken, Peter Franken, here in the 61. And then why 61? Lasers, exactly. Because in 1960, the laser was demonstrated, right? So right away, Franken demonstrated in a Physical Review Letters paper, he demonstrated the process of second harmonic generation. So basically, what he was doing, he was actually using a ruby laser focusing on a quartz crystal, and the ruby laser operates at 694 nanometers, and then, of course, quartz crystal is completely transparent. And then when he was focusing this reddish light in the crystal, he was actually seeing also some blue light at 347 nanometers, exactly half of the wavelength, the double of the frequency. And the way, of course, at that time, in the 60s, the way he measured that was by using a prism and a photographic plate, right? And here is the spot for the excitation laser, and here is the spot for the second harmonic. There's no spot, right? According to the history, people say that the editorial office of Physical Review Letters thought it was a dirty, and then a mistake, and then they clean it, right? We don't know if it's true or not. I think it's true because it's not there. If you take the PRL, you don't see the image of the spot there, right? So this is actually the birth of the nonlinear optics as a separated area. So this experiment is what is considered today the birth of nonlinear optics in the sense as a separated area in optics, okay? One of the pioneers in nonlinear optics is Professor Blumberger, who actually got the Nobel Prize in the 60s or 80s. And he was the one who actually formulated several optical processes. So he was actually the one that was doing semi-classical treatments for nonlinear susceptibilities and explaining several optical phenomena. But before that, way before that, okay, it's a school, right? So people that know me know that I go for the basics always, right? I have some students that I taught here, so they know me already. So that's how it goes. Okay, the first module to understand light-matter interaction is the Lorentz module, right? So you treat the media as an electron in a spring, right? As a harmonic oscillator. So basically, so that's what we call the Lorentz model. So basically, here you have your atom, here's the electron, and then the bounding here is by a spring with a constant k, and of course we know the resonance frequency of that system, and so that's how we're going to model our atom, right? And then, so here is the harmonic term, and here would be the force that we are applying to our system there, that of course in this case is going to be treated, so that's the electric force, the charge times the electric field, and of course since we are dealing with light, it has to be an oscillating wave in a given frequency omega. So in order to use this kind of approach to understand light-matter interaction, what we do is that we use this approximation here in which the electric field of the light, right, that is exciting our atomic system is much smaller, the amplitude is much smaller than the interatomic or intermolecular electric field. So the electric field that binds the electron to the atoms. So in this case, it's basically, okay, the amplitude of the light is not in the same order as the electric field of, in the internal electric field of our atom. All right. Okay, I'm just going to go very fast here to the math. I'm going to give you the slides, so don't worry too much. But I know that several of you guys know these things already. But anyways, okay, the steady state solution for this is this one here. So that's displacement of the electron. Then x0 is actually given by this. So of course, as the frequency of the light approaches the resonant frequency, we get a higher displacement, which of course means that we have a higher polarization. So the dipole moment that we induce in our atom is bigger. So the dipole moment can be written as this here is the charge times the displacement. So the dipole moment is given by this thing here. So that's the dipole moment that we're actually inducing in the material using this model. Okay, so if we know the dipole moment, we can calculate the polarization. So basically the polarization is the number of atoms we have, the density of atoms, times the dipole moment. So here's the polarization, and don't worry too much. There's a constant here, which actually depends on the frequency, times the electric field amplitude. Okay, so that's exactly what I was talking before. So the polarization then is proportional to the electric field. So that's linear optics. So every time we use a light in such a way that the polarization induced in the molecular system is proportional to the electric field applied, that's linear optics, right? And with that, we can get, so we can, of course, this E, so whatever is here is the susceptibility. So the susceptibility is given by this thing here, which, of course, is a complex number, is a complex quantity. And then, as we know for our electromagnetism courses, then we can define a complex index of refraction from where we can get the index of refraction and the absorption of the material. So basically, the index of refraction is related to the real part of chi, the susceptibility chi, and the absorption is related to the imaginary part of chi. So we all, or some of us, we have done that before. So it's not very hard to actually get, from this point of view, the index of refraction and the coefficient of absorption, right? So that gives us the dispersion of the refraction and the dispersion of the absorption, right? So here is how the index of refraction depends on the frequency and how the coefficient of absorption depends on the frequency. The only thing I guess I could skip all this math, right? Which is not very hard. And then just show you the following. Of course, the index of refraction depends on the frequency, right? Depends on the color. But it does not depend on the amplitude of the electric field. It doesn't depend on the intensity of the light, right? There is no big E here or there. So N and alpha do not depend on the light intensity. Okay, what happens then if we go for the nonlinear interaction? So what's the nonlinear interaction regime? So it's basically where the radiation electric field is on the same order of magnitude of the interatomic electric field. So in this case, the light that I'm using to excite my atomic system there is on this, at least on the same order of magnitude. I don't want it to be higher. It's possible, but I don't want that to occur, right? Otherwise, I will ionize the atom. That's something else. That's another part of nonlinear optics, okay? But okay, that's how we get nonlinear optics, as I mentioned before. So if I have femtosecond laser pulses, that's easy to get. So how high should the light intensity be for you to be in this regime? So let's make an example here. You know, as a physicist, we go for the simple thing. So we have here this hydrogen-like atom. So that's the charge of the electron. And I will take the radius as 4 angstroms. I'm not taking the hydrogen, which is half of an angstrom, just because if you work with condensed matter, you usually don't work much with nitrogen, or with a hydrogen, right? You work with something which is bigger. So just to give you a feeling. So in this case here, the electric field, the atomic electric field is 10 to the 8 volts per centimeter. So that's the interatomic, let's say, electric field. Okay, that's a laser, continuous wave laser. That's the laser being focused in a given region, and that's the radio of the focalization, the spot of the beam in the focus, right? The W0. So let's take a 20 watts laser. Okay, and focus that 20 watt laser in 20 microns. So 20 microns, it's much thinner than our hair, right? The hair is about 150 microns. So 20 microns, it's like 1/5 of a hair, something like this. 20 watts, that's a lot of power, right? If you place your hand in front of a 20 watts laser, it's gonna burn, for sure, right? Even if it's like a 1 millimeter, okay, beam spot. So okay, if I'm focused this laser, I can calculate the intensity by using, basically by dividing the power by the area, and then I get something which is 310 to the 10th watts per meter square, and then I use the pointing vector, or the intensity, the relationship between the intensity and the electric field. I plug all the constants, and then I get this electric field magnitude. So 10 to the 4th volts per centimeter. So what I'm saying here is if I'm focusing 20 watts in 20 microns, the electric field is only 10 to the 4th. So it's still 10 to the 4th times smaller than the one you would need. So in this case, I wouldn't have nonlinear optics. So in order to get nonlinear optics, you really need very intense laser pulses. So if I take here the example I gave you before, 100 gigawatts per centimeter square, and then if you back calculate, you get here 10 to the 7th volts per centimeter. And then now you are close, right? So if you are using gigawatts, then you are close. Of course, if you are working with a much bigger molecule, for sure, the electric field's got to be smaller than 10 to the 7th, 10 to the 8th. So just to give you an idea on which kind of lasers you need to see nonlinear optic phenomena. Again, just a small detail. In this regime, where we have electric fields on the order of 10 to the 8th volt per centimeter, which means intensity on the order of hundreds of gigawatts per centimeter square, that's what we call perturbative nonlinear optics, meaning that it's on the same order, but it's not bigger, so I can still apply perturbation theory. If you go with intensities, if you go for terawatts, and then the electric field's got to be something around or bigger 10 to the 9 volts per centimeter. So in that case is what we call extreme nonlinear optics. So in that case, perturbation theory does not apply. You can still study. There's lots of stuff to do in extreme nonlinear optics, but that's something different. Okay, and then if you want to apply the same picture as the Lorentz model before, for understanding such nonlinearities, So how do we do? So we do the same thing, but now the idea is that with the electric field of the light, we're not only moving the electron a little bit for the equilibrium. We are moving the electron considerably from the equilibrium. So basically now, the potential is not harmonic anymore. So the potential that before, right, was squared potential, given by the Hooke law, now it's got to be distorted. So it's got to be a enharmonic potential, right? And then that's why we include this term here. So that would be the harmonic potential, right? That's going to give you the harmonic potential, but then we have to include an anharmonic term to the potential, just to distort a little bit the potential there. So that's how we solve this. So now our force, right, restitutional force, is the harmonic term plus this enharmonic term. And then, of course, if we calculate the potential, we all know how to do this. You have the harmonic one, which is the parabolic potential here, plus a cubic term, which kind of distorts a little bit the potential. And then, of course, it depends on the symmetry of the material you are trying to model there. So if it's a non-centrosymmetric material, it means that for one side is different for the other one, you go for the cubic terms. If it's asymmetric, right, you go for another term here, which gives you x to the fourth, and then it's got to be enharmonic, but it's got to be symmetric. And then it depends on what you're doing. Here's just an introduction, right? Okay, so we know now that we need, in nonlinear optics, to solve the enharmonic oscillator. Okay, that's not trivial, but it's easy. So again, the electric field is given by a wave. We are treating light with a given frequency omega. We're going to use the perturbation method here. So how we're going to do that? First, we are going to assume that this term, the perturbation term, is much smaller than the harmonic potential there. Just so perturbation theory applies. So we are disturbing the potential, but we are not destroying the potential. We're not disturbing too much the potential. I will skip all the passes for using perturbation theory, but basically what we do is that we expand the solution in the first order approximation, second order, third order, so on and so forth. So that's how we solve this. We use the perturbation method, and you solve this very easily. So here, the first order solution, x to the 1, is actually made by removing the anharmonicity. So basically, you make A equal to 0, and then you solve. That's exactly the solution we had before for linear optics, right? That's exactly the same problem. So in first order, enharmonic potential is the harmonic one. That's exactly what we're saying there, right? So as the first approximation, the enharmonic potential is the harmonic one. So the enharmonic term is 0. Okay, you plug 0 there. We know that already because we solved it before. I'm just using a different nomenclature. So that's exactly the solution we had before for x1. In second order, so the first approximation for the enharmonic term, instead of using ax squared, we use ax1 squared as the first approximation. We plug it there, and we solve everything, and then we get here that in second order, the displacement, okay, it has these denominators there, which are related to the resonance frequency, so on and so forth. But as you can see here, it's already dependent on the amplitude of the electric field square, meaning that it's dependent on the intensity in this situation there. Okay, let me try to go a little faster. Then we can write the polarization. So the polarization is the dipole times the density of atoms. And then, of course, x in this approximation is x1 plus x2, so on and so forth. If we plug here the numbers, you have the first order nonlinearity, linearity, I'm sorry, plus something that goes with the electric field square. So that would be the second order approximation. So if you keep on doing this, you will get that the polarization would be in the first order, or in the linear optics, it's got to be proportional to the electric field. And then there's a second order term, a third order term which is proportional to the electric field to the cube, so on and so forth. So that's what we call the nonlinear polarization. And if you are familiar with electromagnetism, so basically now you plug this polarization there, and then you solve the nonlinear optics in electromagnetism. Okay, let me just show you some consequences of this polarization that depends on the electric field in a nonlinear manner. So for instance, let's suppose that now, instead of exciting the material with a given monochromatic frequency, we are using two lights in two different frequencies, omega 1 and omega 2. So in the harmonic oscillator term, we have this guy that goes with the square of the first order solution. And then, of course, if you look at that, here, here, you see that then we have to square, we have a square of the electric field. But then, if the electric field is like this, we have now terms which will be in the double of the frequency, because you have this term squared plus this term squared plus the cross terms. So you have then frequency components in your nonlinear polarization that will be on the second harmonic of omega 1, the second harmonic of omega 2, the sum and the differences of the frequencies being generated. That means that now the polarization that I'm inducing, so in the linear optics, the polarization is always in the same frequency of the applied electric field. In the nonlinear optics, only considering second order, the polarization might be on the double of the frequency, or in the sum, or in the difference of the frequencies. So you are inducing a component in the polarization that actually oscillates in different frequencies from the fundamental one. Okay, Lorentz is the same Lorentz, right? Is the Lorentz from the Lorentz force, is the Lorentz from the Lorentz transformation. So he actually got the Nobel Prize in the 30s or 40s for explaining the Zeeman effect, if I'm not mistaken. But in 1910, I guess, he proposed this model just until here, the harmonic term, to actually explain the light-matter interaction and to explain the index of refraction and absorption. Of course, he didn't have the motivation to consider an harmonic term. If he had considered an harmonic term in 1910, he would be alone the father of nonlinear optics. So it was just a lack of motivation, maybe. Why do we care about a anharmonic potential, right? So he would be the father of nonlinear optics maybe 50 years before. I will try to go very fast through these parts here. So this first part was just to give you an idea of how, using a very simple model, we can understand this nonlinear polarization. But in fact, the nonlinear polarization, if you want to understand the optical phenomena, you actually enter the nonlinear polarization in the wave equation, in the electromagnetic wave equation here, in the source term, so in your right hand side, right? So here is the vacuum or the light propagation, and here's the light-matter interaction. And then now, in the electromagnetism, by plugging here the nonlinear polarization, you can see all the nonlinear optical effects taking place. So that's exactly what Bloomberger did in the 50s or the 40s. So the first term is the linear process. The chi2 is related to some frequency generation, difference frequency generation, second harmonic generation. Chi3 effects, third harmonic generation, carry effect, and other nonlinear effects. Just to give you an example here. So quickly, so so again, let's see. So for those of you that are not familiar, so if we go for the second order there, so basically what I'm saying is that in this case, I'm exciting a material that has a chi2 with a frequency omega, and on the other side, I have the same frequency as the fundamental frequency, but we also have a frequency that goes on the double of that frequency, right? And the reason for that is because the nonlinear polarization, it goes with the electric field squared. And since the electric field is described by sinusoidal wave like this. Of course, we have something in the double of the frequency, but also we can have something. So if you actually do the math here, you see that if you have a material that has a second order, you always have the second harmonic generation, but you also have what people call optical rectification. So this term here gives you zero frequency. So basically, you excite with light, and then you have a DC field. Okay. Again, just to give the merit, here's some picture just to illustrate. So in those tweezers, you have nonlinear crystals. Those are microscope objective, focusing the light in that crystal, and which are generating second harmonic. So for instance, this laser here, it's at 1200 nanometers, right? So it's generating light at 600. This one here is 1000 nanometer, so it's generating light at 500 nanometers, more or less. This one is at 900 nanometers, so it's generating light at 450 nanometers. So that's real. I mean, that's something that we can do very easily in our labs nowadays. So even some lasers that you buy, they have already second harmonic generation crystal inside. So when you buy a neodymium laser, right? So neodymium operates at 1064, so it's in the nanometer, so it's in the infrared. But you have already inside the laser a nonlinear crystal that generates the green light that you see coming out from the neodymium. So just to give just as a curiosity, that's a nonlinear crystal in the Lawrence Livermore lab. You see the size of the crystal, which a very nice conversion efficiency. Again, so a very easy way to see second harmonic generation then is this photon pictures in which two photons are destroyed and two photons at the frequency omega are destroyed and two photons at the frequency 2 omega are created. There is no absorption. Okay, that's something that I forgot to mention. But when you take one of those crystals, they are completely transparent to the frequency omega. So that's not fluorescence, right? That's not that I'm exciting to a given excited state and then is relaxing and emitting light at the green. That's not what's going on there, right? It's a nonlinear polarization that is inducing light in another frequency. Or in this picture here, is basically two photons are being destroyed and one photon is being created. And of course, energy conservation holds. Okay, there's no problem. Something else that if you go now for the third term, let's take here the third order process, just to give you an idea. There are several other processes such as third harmonic generation, but I'm going to go only with this, this one. So let's suppose that for this material here, I don't have a second order process. So chi2 is equal to 0. I only have chi3. So here's the polarization, chi1 plus chi3. So this guy here, it's E squared. So E squared is proportional to the intensity, as we know. So that's got to be chi1 times chi3 E squared, which is actually E, or proportional to E, times E. So now I can call this guy here, this quantity, as an effective susceptibility, right? Like this way. So the effective susceptibility now is not a constant. It depends on the intensity of the light, right? So, and then of course we know that the susceptibility is related to the index of refraction by this relationship here, from which, after doing some easy calculation, so again, this is the complex nonlinear index of refraction, from where you can get the refraction and the absorption. And then, what's the final result of this thing here? Because now the susceptibility depends on the intensity, the index of refraction depends on the intensity of the light, as well as the absorption, right? So what I'm saying now is, before, we had an index of refraction for a glass, I don't know, 1.5 in a given wavelength, right? But it doesn't, as we know even from high school, that does not depend on the intensity of light, right? So the index of refraction is a constant. It depends on the color, but for a given color, it doesn't depend on how intense is your light. Okay, that's before nonlinear optics. After nonlinear optics, there is this term here, which is called nonlinear index of refraction, which is somehow related to the real part of chi3, which gives you a dependency of the total index of refraction on the intensity. So if N2 is positive, it means that as as higher is the light intensity, higher would be the index of refraction, right? At the same time, the same happens with absorption. So that's the beta, which is related to the imaginary part of chi3, and that's proportional to the intensity. So that means that if you have a sample which is, let's say, transparent, right? So let's suppose that alpha 0 is almost 0, and then beta is positive. And then you excite with very intense light, it becomes opaque. It has some additional absorption. So the absorption, it can, of course, it can increase the absorption or decreases depending on the sign of beta there, which is the so-called two-photon absorption coefficient for chi3. Okay, so again, that's just something. I'm going to try to explain why this is called two-photon absorption. So that's the same slide as before, but with more details. So if we now consider, just let's have a look only on the nonlinear absorption, this dependence on the absorption with the light intensity. We can calculate the cross-section. So basically, the absorption cross-section is the absorption coefficient divided by the number of molecules, the density of molecules. So that's a way of normalizing, let's put this way, the absorption, right? So you take the absorption coefficient and you divide by the density. Okay, that's easy, right? Now I plug this thing here. So that would be the linear cross-section plus this term here, which is the nonlinear cross-section. Okay? Usually people like to express this in photon flux. So you multiply and divide by the photon energy here. What I'm doing here is basically, instead of expressing the intensity in watts per centimeter square, when I divide the intensity by the energy of a single photon, that the intensity now is on the number of photons per time per area, right? So that's basically the flux of time per unit of area, right? So the flux of time. So that's another way of saying this. So that's the standard, and then this thing here is what we call the two-photon absorption cross-section. So it's basically the two-photon coefficient times the photon energy divided by the density of molecules or atoms we have in our system. The excitation rate, so how I can excite a system is actually given by this quantity here times the flux of photons, right? So once I know the cross-section, right? Once I know the absorption cross-section, and if I want to know how many transitions occurs, I just have to multiply this thing here by the flux of photons. So, okay, but now in the nonlinear regime, it has already this part. So if I substitute this thing here in here, you see that there is this, that's the linear term. What this is saying to us? Basically, it's the same in the linear regime. You have more transitions as you increase the intensity, right? Or the flux of photons. So, right, that makes sense, right? So in the linear optics, if you use more power, you have more transitions. We are used to that. In the nonlinear regime, up to the second order, or the third order nonlinearity, to the second order in the absorption here, you see that the number of transitions, the transition rate, it goes with the flux squared. That's why it's called two-photon absorption in this picture, okay? So because the transition rate, it goes with the flux of photons squared. In fact, and now for the ladies here, for the young ladies, so have you ever heard about Rupert Marie? or Marie, I don't know. Maria is German, so Maria Guppert-Meyer. Huh? Yeah, actually, she was actually the second woman to get a Nobel Prize in physics. And the third one, we know, right? Third one we know. Is this year, right? So Maria, actually, the first one we know also, right? So we know, we know the first one, it's Curie, Marie Curie. We should know the last one, which is the one from this year, right? Donna Strickland. And that's the one in the middle, actually. So that's the second woman to get a Nobel Prize in physics. Yeah, that's German, right? I would love to pronounce that correctly. Anyways, it's something like about elementary processes with 2-photon quantum jumps. Are you reading the German there? I'm translating correctly? No, right? I'm doing a mistake. But it's something about mit is with, right? Zwei is 2. Quantum is sprungen. Yeah, so it's like quantum jumps, right? Actually, but, okay. So, she was a theoretical physicist, and she was actually studying nuclear physics. And of course, she was interested in more than one body interaction. That's why she studied this process of several processes involving multiple interactions. And then in the 30s, actually, she proposed the mechanism of 2-photon absorption. So way 30 years before the laser. So 30 years before the laser, she knew already that if we had enough intensity, we should be able to see a process in which 2 photons would be absorbed by a given material at the same time, promoting the atom from the ground state to the excited state. And she used the semi-classical treatment. That's quantum mechanics. I guess I'm going to skip all this. But that can be done. It's in there. I'm going to give you the PDF files. You can also look for nice books in nonlinear optics. They're going to have all the details. But basically, that's the Schrödinger equation. That's the Hamiltonian there. So the interaction Hamiltonian, which is this guy here, is the Hamiltonian from the free atom plus the interaction in the dipole approximation, right? So that's this thing here. And then you assume a monochromatic wave of your electric field, right? And then you solve quantum mechanics, right? So there you go. And then here's the equation we have to solve. So basically here, we write the solutions for that equation as a linear combination of the solutions for the free atom. As we know, the eigenstates for the free atoms, they are a complete base set, so you can express everything in the proper way. And then you get this equation with the amplitudes of probability that appear there. And then, but that's a kind of interactive kind of solution, right? So in order to have the solution in first order, so that's again perturbation theory. So in order to get the solution in first order, you gotta know the solution in the previous order. For instance, in order to have the solution for the first order approximation, you have to know the solution in the 0 order approximation, so on and so forth. So you have to study first without the free atom, and then the first perturbation, and then you solve everything, and then you get that result, and you do it again, and you do it again, and every time you do it, the math gets bigger, right? So that's why people usually do up to 2 photons. I never did it up to 3 photons. I'm not gonna go again, but so linear absorption. For the linear absorption, I wanna solve this equation with n equal to 1, okay? And I will assume that at the beginning, all the system is in the ground state, there is no excited state. And then you do the calculation here, and then you calculate here the amplitude of the probability of a molecule being excited by the electric field for your light in the linear absorption regime. Then you actually get the amplitude of probability that this transition occurs And then the probability is actually given by the square of the amplitude of probability, as people that did quantum mechanics knows. And here, and then you get this thing here, which is the probability. So as you can see here, that's that's a good result to discuss a little bit. So as you can see here, the probability of a transition from the ground state to the excited state, it goes with the intensity. You see, the amplitude of the electric field square here, which is proportional to the intensity. So as higher the intensity, as higher the probability. And also, it goes with the time, right? So if you wait long enough, you see that event happening, right? It depends also on some transition dipole moments. And also, that's conservation of energy. You see, you have a delta function here, which means that you only have the transition from the ground state to the excited M state if the omega of the light is equal to the omega of the transition, right? Okay, the transition only occurs if the electric field frequency is the difference in energy between the ground and the excited state. That's given here. Then we get this. I'm just replacing the Dirac delta function here by the line shape, but that's what we get. And then, so just to make a link with whatever I mentioned before, that's the probability. And the probability is proportional to the time, right? So the probability rate, I can define then a probability rate, which is the probability divided by time. So how many times it occurs by time? How many times it occurs? How frequent, right? Okay, thank you very much. Right? So I basically divide it by time. So that's the transition rate. So that's the rate of transitions of one photon transition from quantum mechanics. And as you see here, it's proportional to the intensity. And then whatever is here, from the quantum mechanics point of view, is what we defined as the cross-section, right? Or first principles, just coming back, so you see. Right? The transition rate is proportional to intensity. And whatever remains is what we call the the cross-section, coming back from quantum mechanics point of view. And now, if we go for 2 photons, as I mentioned before, now we want to solve this for 2, right? So n now is equal to 2. But then, in order to do this, in this part, I need the solution for 1. So I need the 1 photon solution. That's what I told you before, that now it's getting complicated and complicated. Because, you see, now I need to use this solution here and plug it in the new equation, and then I get the second-order solution. And then, of course, when I go for the third-order solution, the 3-photon absorption process, I need the first, the 1 photon, the 2 photon, and then the equation grows and grows and grows. That's more or less what Maria Guppert-Meyer did. Okay? So we know already this one here for the previous calculation. You redo everything. So in this case, that's the nomenclature. So there's the ground state. I'm going to the excited state, and might be an state in the middle there, which is not being excited. Okay, so I go from the ground state to the excited state by 2-photon absorption. You do the math, and then again you get the probability, which again is a function of time, as expected, right? So if I wait long enough, I have the transition happening. But you see now, E squared is the intensity. And there's a square outside, so it's proportional to the intensity squared, right? Okay, I can't resist. Which is the simple picture that I showed you before is exactly what we got. So the probability rate, the transition rate is proportional to the intensity squared, from a simple point of view and from a more elaborated one. Okay, so here, so now that's the transition rate, And this is, so the transition rate is again the probability divided by time. And as we can see from this thing here, it's proportional to the intensity squared. So in the case of a two-photon process, this is the two-photon absorption cross-section, which is given by this crazy equation here, which is not that complicated, but it depends on the transition dipole moments. It depends on the frequency. And again, it only occurs when two photons are in resonance with the energy, or with the frequency from the ground state to excited state. So conservation of energy again. So everything is very well established, okay? If you keep on doing, that's what you get until 4-photon absorption. Okay, so that's exactly what you can get. So you see, for a 1-photon absorption, the transition rate is proportional to the intensity. For two photons absorption is proportional to the intensity squared. For 3 photons absorption, proportional to the intensity to the cube, to the fourth, so on and so forth. So, and then of course, it's a nonlinear optical process. So usually what happens is 2 photons is much more probable than a 3-photon. So you gotta be in resonance, and of course, it's much rare to see these processes than the other ones over there. Again, so the first demonstration of a 2-photon absorption also happened in '61, right? After the second harmonic generation, again because of the laser. So that's by Kaiser and Garet. So basically what they did, they were using this crystal here, calcium fluoride doped with europium. So basically they were exciting that crystal at 400 and something nanometers, and they were getting light, at 600 and 700 nanometer ruby laser. Here, they were exciting here, and the material was completely transparent at that wavelength, and then they were getting light being emitted in the blue at 450 nanometers, right? And the material is transparent. So basically, it's exactly this picture here. 1 photon, that's the ground state, that's the excited state. If you consider only 1 photon, no transition will occur in the linear optics regime. So there's no chance, right? Because the photon energy is smaller than the required energy to promote the transition. But in the case of the 2-photon absorption, you can think in the quantum mechanical point of view, is that the flux of photons is so high that the probability of 2 photons being absorbed at the same time by the molecule is reasonable, such that they can promote the molecule or the atom from the excited state to the ground state. From the ground state to the excited state. And then, if it's a fluorescent material, you see the emission, the corresponding emission. And you can actually prove that this is actually related to that. So basically, just another remark, then I have to change my file there. This is like winning in the lottery, right? So the lottery in Brazil is with 6 numbers, right? I guess. So I guess the chances are 1 in 50 million, right? Win. So if you just buy one thing there, your chances are 1 in 50 million. But of course, if you buy 50 million cards, for sure you're going to win. Of course, doesn't make sense because you're going to use all the money of the prize to get it. That's exactly what's going on here, right? In a femtosecond laser, the flux of photons is so high that you have a chance that 2 photons hit the sample, hit the atom exactly at the same time, in such a way that they transfer the energy and then you go to the excited state. That's one way to see it. If you want a copy of this presentation, you can visit our webpage. There's some marketing here, right? You go to photonics, ifsc.usp.br. There is a link for presentations. It should be there, only the first one, not the second one. I didn't have time to put it there, but I will do it till tomorrow. But you don't have to remember. right? Because we have Google. And then you just go to Google and you write photonics USP. You just have to remember photonics, and you just have to remember that you are at the University of São Paulo or that you are at IFSC. And if you just write this, or it works in Portuguese too, right? And then we are going to be the first link. And then you go there and you can get this presentation. That's the end of this first part. I guess I did it kind of too fast. Maybe I can take questions to this part right now, and then I move to the next one, like half an hour today, half an hour tomorrow.
Thank you. Thank you, Cleber. I have a very fundamental question, actually. Can we compare a photon to a very short pulse?
I'm sorry.
Can we compare a photon to a very short pulse?
Can we compare photons with very short pulses? That's exactly what we're saying? Can we compare photons? In my way of, there's some feedback, I guess. In my way of seeing, so a very short pulse is a bunch of photons, right? So I guess I think what you have in mind, thinking about, I don't know, like the duration of the pulse, right, is so short that you have just a single photon, but that's not exactly what's going on there, right? Because in order to get a ultra short pulse, you have to have different photons with different colors that are kind of combining and give you that interference that gives you the ultra short pulse, right? Okay. So yeah, I don't think so.
Okay. Thank you.
More questions?
Meanwhile, I will try to find my other file.
No more?
Hello there. So first of all, thank you for your presentation. My question is pertaining to the very first part when you were talking about short pulses in comparison to longer pulses. And I'm sorry if this seems like a very lay question, but I didn't quite understand why exactly when you have a shorter pulse, like you have higher intensities on a shorter time. Yeah, that's intuitive. But why exactly does it, like when you show the graph with the frequency on the x-axis, like you get what I'm saying, right? It is broader. It is distributed over a broader range of frequencies, whereas when you have a longer pulse, you said that it is approximately monochromatic. Yeah, like the graph is like.
If it's if it's really if it's a continuous wave, a perfect continuous wave pulse, then it's perfect monochromatic, right? Because imagine like a single, if you have a single frequency, that's Fourier transform actually. If you have a single frequency, a single color, then your laser can be described by a single sinusoidal wave, right? In a single frequency. So if you take the Fourier transform of a sinus function, that's gotta be a delta function at the frequency of a sinusoidal wave, right?
Yeah, I'm still getting there in my physics course. But my question is, like, why exactly? Why when you have a shorter pulse, it needs to be distributed over a broader range of frequencies?
So let's say physics 2, second year.
Yeah, I'm taking that course.
You look young, yeah. I used to look like that, like 3 years ago. I don't know what happened, maybe 10. Okay, so physics 2, that might be a good starting point. So remember when we were beating acoustic waves? I guess everyone did that sometimes in the lab, right? So you have like one thing, So you have like two different resonators, acoustic resonators, right? One with a frequency of 450 hertz, and another one at 450 plus something, very small. So if you take that one, just a single one, and you hear the sound, that's a la, I guess, right? La, I think is a single one. And then if you take another one in a different frequency, what do you get? You get a wong, wong, wong. That sounds good, right? Because you have the beating between two frequencies that are in phase. So they have a phase relationship, right? But they don't have exactly the same frequency. But that's only for two frequencies. That's what we call amplitude modulation, right? It goes like, that's how people tune musical instruments, right? Or even nowadays in our cell phones, you can do this, I guess. But anyways, coming back. Okay, so but in that case, you are only beating two frequencies, right? And then you are already having some confinement, temporal confinement of your acoustic wave. Wom, wom, wom. Then now, you can do that nowadays in Mathematica, for instance, right? That's very easy. You go there in your computer and do it. Then you start to beat in like different frequencies, several. And then if you add different frequencies, all with some phase relationship, you get a beep, 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 because you are now adding more and more and more frequencies. Okay, I have to come back to the other one. I changed it already, I'm sorry. The other one.
Yeah, I think I should have asked this question a little earlier.
No, it's okay. It's totally fine. I love it. Yeah. There we go. Oops. And this picture, what's her name?
Eduardo.
Eduardo. Du. That's exactly what's going on there. So you see, if you have more and more frequencies, so if you have only two frequencies and you beat them, so two frequencies would mean like two of those waves. And if you beat it, you get the amplitude modulation. But then if you have more and more and more, for instance, this one at this point, see, this one is positive and this one is a little bit negative. So they will have a small number. But this one is also negative, the other one is negative, and then if you have more and more, you see, they will kind of cancel each other. And then you will only have a constructive, let's put it this way, interference in a given time. You see? And that's why you need more colors to do a shorter pulse. And that's why you need more colors to do a shorter beep or an acoustic wave from a feeling kind of thing, right?
I get it now. Thank you.
Okay.
Any other questions?
Hi.
Hey.
I would like to ask a question about the pulse, the form of the pulse that when you were saying the femtosecond pulse that goes like 8 times up and down. Yeah, that one. This is a single femtosecond pulse, right? Some laser sources use like Q-switched and mode-locked pulses. So this comes like several pulses like that in an envelope with amplitude. I'm trying to imagine the form of this.
Oh, yeah, okay. So if you have a Q-switched mode-locked laser, so usually when you have Q-switched and mode-locked lasers, the Q-switch is in the picosecond regime, right? So that's much longer in time.
Yeah.
So that's almost, okay, that's not right to say, but for me, that's almost CW laser, right? So that's there's a single color. So I guess we are like doing some, it might be a confusion here. So that would be for a single pulse in 10 femtoseconds, so the electric field of that pulse, right? So that would be, if you compress that in time, that would be a single pulse. But the electric field, the intensity is this thing is squared. So it goes like this, and then you square, right? So if
this is something else. This is not like that train of pulses.
This is not a train of pulses, exactly. That's not the train of pulses. That in a Q-switched mod-lock laser, that would be the electric field, not this one, right? Because this is too short, right? Because that is in picosecond. So that would be one single picosecond pulse. That would be one single picosecond pulse would be something like this, but much more oscillations, right? Because it's much longer. But that's not the Q. That's not. And then in that case, you have like several pulses for the mode lock.
Yeah.
Everyone. So there's one pulse for the mode lock, the other one. Everyone looks like, aspas, like this. But then you have a Q-switch envelope on top of this that's gonna give you the pulse train. So it's a different thing.
This is like looking into a single femtosecond pulse and the oscillation of
Exactly.
Okay.
If it were a picosecond pulse, it would be something similar, but with much more oscillations.
Okay.
Like a single picosecond pulse, for instance.
Okay, thank you.
Hello, my name is Ronald. Thank you for the great lecture. I just was wondering, you said femtosecond is 10 to the minus 15, right? And I think I heard there are some laser pulse 10 to the minus 18, and I guess it's attoseconds, and could be later zeptoseconds.
Yeah.
So what would be the meaning of having shorter and shorter laser pulse?
That's a good question. I love those kind of questions, the crazy ones, right? So I'm just getting crazy questions here, just hard ones. No, the one there, the one here. So yeah, an attosecond pulse, it's 10 to the minus 18. So that's really short, right? I mean, it's like, of course you can get like hundreds of attoseconds, which is maybe 10 times shorter than like, I don't know, one femtosecond. So I guess one thing I can tell you is the following. Have you ever heard about attosecond pulse in the infrared or even on the visible? No, right? They are always in the ultraviolet, right? Because otherwise they don't oscillate. And then there's a big discussion if a very, very short attosecond pulse. So how? Because you see, like the pulse is so short that if you are in the infrared, if you were to create a attosecond pulse in the infrared, it wouldn't oscillate at all, because there is not enough time for an oscillation with the frequency of the infrared. So people move to the blue, to the ultraviolet, because in the ultraviolet the frequency is higher. Then in an attosecond you might have 1.5 periods. And then that's considered, so man, that's cutting edge science, right? So that's like, so people are considering that you have to have at least one oscillation of the electric field in such a way that you can consider that a pulse. So maybe 1.5. So when you go for attoseconds, that's another physics, actually. That's something different. It's very much related to, usually you need femtosecond pulses to generate attosecond pulses, right? We have some generation of ultraviolet here in our lab for like aiming at attosecond pulses, but we're not actually quite there. We're just generating a soft X-ray, deep UV, 30 nanometers, so on and so forth. But so that's the point. So it wouldn't make sense to talk about a attosecond pulse with this kind of colors, with this kind of frequencies. So it's a different kind of stuff. But I guess that gives you an idea, right?